there. This is engineering SWML 13. Today we're going to talk about model compression. So our base model, the one that we have originally, is self-training with Gaussian process classifier. Its accuracy was 94.12%. F1 score was 0.127, and the size was 3,194 kilobytes. So this is where a major problem comes in, because if you want to deploy this on embedded systems, if you want to deploy this on low-end hardware, which are resource constrained, this is going to be very difficult and become a problem for us. But then when we carry out model compression, we see that this is actually feasible. So the technique we use here is knowledge distillation. This is where a larger model, which is the teacher, trains a smaller student model. The student model can learn on the teacher's outputs, it can learn on raw data, it can learn on anything, but our goal is to ensure that the part of resource constraintness is catered for while deploying this model. So after we compressed our model, we still got our accuracy as 94.12%. Our F1 score also didn't change, it was 0.9127. But then we see that our model size was reduced very, very much to 1.2 kilobytes only. So we see that this makes it very lightweight, very deployable. It can be deployed on virtual devices, it can be deployed on mobile phones, unlike our base model here, which is very heavy. So that was the size, but then we see that the training time was actually a cost that we encountered here, but it can be overlooked and be overcome in practice. So it is not a major problem here too. So our size reduction versus the teacher, see that it was 100%. So I think this was a very good technique that worked for us very well. Yeah, so I will now pass on to my colleague for the remaining one. Okay, one second. So my colleague, she's, but then I'll be stepping in for her. So let's continue. Audio compression techniques. After we saw distillation, we are now going to pruning. Now pruning, this is where not every feature is going to be able to give us the same importance. So we are going to remove the ones that are less important and keep ones that are very important to us in our model as we compress it. So think of it like pruning a tree, where you remove the branches that are weighing down the tree so that these other important branches can. That's what we did with our model, and we still got the same accuracy as our original one, the same F1 score. But then our size reduced by around 3.4%. It wasn't a very much reduction, but it was there. Training time increased a bit. Yeah, so that was what we did for pruning. Then for quantization, it's basically where we just do numerical precision for our model parameters from float 64 to float 32, from 64 bit to 32 bit. Yeah. So we also got the same accuracy for this one, 0.9412, same F1 score 0.9127. And then we see that our model didn't really reduce in size. It was literally the same thing. So our size reduction was negative 0.0%, actually 0.0%. Then our training time was 0.008 seconds. That, yeah, it's a very negligible increase in time. Yeah, so looking at all these three techniques, we see that knowledge distillation is the one we are going to prioritize here because there is a very big reduction in size for it compared to these other two. These other two could work for us in other contexts, but for this specific one, we are going to go with knowledge distillation. Thank you so much.
Hey everyone, this is Arije Docas, and I'll be taking you through the model compression visualizations. So this slide presents a comparison for 4 model compression strategies applied to a Gaussian process classifier, the teacher model, knowledge distillation, pruning, and quantization. We evaluate them across 3 dimensions: predictive performance, model size, and training time. Let's walk through each. The first chart shows the accuracy, precision, recall, and the F1 score across all the 4 metrics. Every model scores between approximately 0.94 and 1.0. The bars are almost indistinguishable. This is actually the key insight. Compression does not meaningfully hurt the predictive power. Whether you use the full teacher model or a heavily compressed variant like the knowledge distillation, you retain near perfect classification performance. For any real-world deployment, these differences are negligible. Then the next one, which is this one on the top right, the model chart, the model size chart tells a very different story. The teacher model is enormous. Now compare that to the knowledge distillation, which shrinks to just negative 1.2 kilobytes, a reduction of over 99%. That is extraordinary. So pruning sits at around 3,085 kilobytes, almost no improvement over the teacher, while quantization comes in at around 3,194 kilobytes, similarly large. So if the storage deployment footprint is your priority, knowledge distillation is clearly the winner by the massive margin. Then we'll go to this graph on the bottom left. The final chart measures training time in seconds. The teacher takes essentially negative 0 seconds. It is a self-training baseline. Knowledge distillation is also fast at around 0.14 seconds. So pruning, however, is notably slower, around 3.3 seconds, and quantization returns to near 0 at roughly 0.008 seconds. So this means pruning carries a computational cost at training time while delivering minimal size benefit. Quantization and knowledge distillation are both to train, making them far more attractive in practice. So in summary, all the 4 models achieve equivalent predictive performance, but when we factor in size and speed, knowledge distillation emerges as the optional compression strategy. It is the smallest by far, fast train, and loses nothing in accuracy. Pruning offers the worst trade-off: short to train, barely smaller, and no performance advantage. Quantization is compact in training time, but retains the full model size. This is all I had.